All right, so today we're going to talk about section 3.1, which is all about inverse functions. So if you recall from section, or from the last 2 units we've talked about, or 2 chapters, we've kind of talked about more strict functions and kind of like different definitions for each one. And so to start us off with this unit, this section and chapter 3, we need to understand the concept of inverses and some more specifications of functions in order to understand what the main portion of the chapter is on. So we're going to learn all of these different objectives here. So we have some one-to-one functions, inverses, and then finding inverses. Okay, so if you recall from section 1.3, the definition of a function is, given a relation in x and y, we say that y is a function of x for every value of x in the domain. There's exactly one value of y in the range. Remember that plugging in one value for x, you cannot get 2 values of y out. It just doesn't work that way for something to be a function. So you just cannot ever have, plugging in just one value for x, getting out multiple y's. So we use the vertical line test to determine if something is a function, if you remember that from section 1.3. So here's some examples of functions. We have these... So we have this coordinate pair system here, right? Now you notice that these 6's are matching, but since they are in the y's, we don't care, right? So it's 2 different x's that are mapping to the same y value, which is fine. We can have that. We have a function here, f of x equals 3x squared plus 1. That's a function. We know that it's a parabola. And then we have our simple mapping. Whenever we have the circles with the arrows, we call this a mapping, right? You're taking values of x and mapping them to some value in y. So you're going to hear me talk about mappings a lot. And so just make sure that you understand kind of the mapping, meaning this is the function, right? It's taking in these values and outputting something in here. So remember, we didn't want 2 arrows, right? This was not allowed. You weren't allowed to have 2 arrows out of one x, but you can have 2 x's going to one y. That's completely fine. These are some examples of not functions. Here we have repeating x values with different y values, so that's something we can't have. This, if you remember, if we solve it, we're going to get 2 different values for y, right? We're going to get y equals plus or minus square root of x squared. What is that? Right, if we were to solve this, we'd get y squared equals plus or minus square root 1 minus x squared. If we subtract that x squared over, and we can't have that. This is not allowed, right? It's not allowed. So that's why we have to be careful. And this is supposed to be just so that's why we have to be careful. That's not a function, right? It's also, this is a circle centered at the origin with a radius of 1. And so if I were to do my vertical line test, it is going to pass through twice. And remember, that was the issue that we had, was that the vertical line test passing through 2 times is not allowed. Okay, the next thing that we have is the mappings, right? And if we have 2 coming out of the x, right, that's not a function. So these are all examples of not a function. Now, a lot of times in math, we want to keep going farther to be able to classify different functions and talk about a little bit more special properties that they might have. So for something to be a function, there are restrictions on x mapping to y, right? You can't have 2 arrows coming out of x. That's just not allowed. Now, we don't care about the y values in that sense, right? There was never anything that said like, oh, we're trying to search for, like specific, can 2 arrows go to y? Can no arrows go to y? Can 1 arrow go to y? And now we want to ask those questions about the restrictions on y, right? The last time we were worried about x, now we're asking about y. So when a function has a single x and y value mapped together, we say that it's 1-to-1, right? And which means for every x value, there's just one y value. It is simply mapping 1x to 1y. So that's all it's doing. Instead of the possibility from up here of taking 2 x's and mapping them to a single y, that's just not allowed for 1-to-1 functions. And so here's the formal definition of a 1-to-1 function, right? We say a function f is 1-to-1 if for all a and b in the domain, 2 arbitrary elements, 2 arbitrary values, in the domain, if they are not equal, then f of a does not equal f of b. Or you could say if they are equal, then A equals B. Now, it's very, very difficult to prove these kinds of mathematical statements. And so in this class, we're not really focused on math proofs, right? That's really not this course. This is a pre-calculus. I'm trying to give you the foundational algebra skills to go on and succeed in higher level math courses. But if you were to prove that a function is one-to-one, I'm going to kind of show you how to do so. This statement here does require kind of heavy lifting proof methods. So we're not going to prove it now. I'm just going to show you kind of the different things that we can do with this definition. So to show that a function is one-to-one, you must show that the function is first, the equation is first a function. That's the first step. So every single one-to-one function has to be a function. That's the first step. So AKA vertical line test or disproving it somehow. Then you have to show that it passes something that we call the horizontal line test. So now we're having another line test instead. So we call this the horizontal line test. So we have vertical line test is for testing if something is a function or not. And then horizontal line test tests if it is one-to-one or not. So let's say this is a really nice picture. There's various different kinds, more functions. Like there's different classifications for functions later on. And really what this has to do is what we call mappings, right? Now, there's also another term if you were to look up videos or if you look online, this idea of a codomain. And so a lot of times in stuff, and we haven't really talked about it too much now, the range is what we call a smaller section of the codomain. So essentially in functions, we like to classify what kind of values can come out. And so a lot of times we'll just have real numbers, right? Real number solutions. But then after you classify it as having real number solutions, then you specify the range, right? So take a parabola, for instance, right? X squared. If we have y equals x squared, we know that the range is going to be 0, infinity, right? We know that for a fact. But the codomain are all the values that you can hypothetically get out, which is all real numbers, right? You're going to get real numbers out of that value, out plugging anything in, right? So that's kind of the idea where the codomain is a larger space than the range. So that's why when we're describing this in the function notation, they're going to have more pictures and bigger, they're going to specify and say codomain. So a function, right, is a mapping from A to B, A and B. A is the domain, B is going to be my codomain type of thing. And so if I want to specify my range, it's going to be right here in red. So that's going to be the range. And so those extra dots are just to show that there can be more values, right, that we're expecting. It's the kind of numbers you're going to get out at the end. One-to-one is what we were just talking about, and it means for every x and y, right, they map together. But the same thing is that you can have a smaller subset, which is going to be your range. And then we also have onto, which we're not going to discuss in this course, but it is going to come up, I'm sure, in later on courses. This just simply means that there is no extra values. So you really just have a domain and a range, and it is also going to be similar. It's like a function, but instead of having extra values, right, the codomain and the range are the same thing. And then the bijection, which is like the ultimate strict function, is also, again, where the codomain and the range are the same thing, but they're also that one-to-one. So bijection is one-to-one and onto function. That's really what it is. It's just the both of those kind of stitched together. And onto really just means that it doesn't have any extra elements in the codomain versus the domain versus the range. So that's really what it means. So anyway, for us, we're just interested in the one-to-one, meaning that for every x, there's just one associated y. So here's some examples of some values, some one-to-one. So notice here that every single x has a corresponding y, right? They're all different. Here is something, here's another function. It passes my vertical line test, so it is a function. Okay, so that's the first step. My next step, I want to see if it passes my horizontal line test, which it does. So this is also going to be a function. All right, let's answer this question. Is this one-to-one? So remember, we need to first test, does it pass the vertical line test? Yes, it does. Does it pass the horizontal line test? No, it does not. It hits the function 3 times. So we have to be careful about that. So this is not 1-to-1. Okay, now we have this function. Let's see if this one passes, and passes the vertical line test, and it's going to pass the horizontal line test as well. Remember, the horizontal line test is the same thing as the vertical, but it's a horizontal line. Okay, let's do some fun proofs. So like I said, this isn't really a proofs class, and it's not requiring you to have a strong foundation, but this is a problem in the textbook, and it's definitely going to be a problem you should see in ALEKS. It's pretty much a classic pre-calculus problem. And so we are going to prove that a function is 1-to-1 without graphing. And we're going to use the definition to show that this function here is 1-to-1. So here's the general idea of proofs, is that you kind of want to show that the left side equals the right side, or you want to go from here to here. This is my need to show statement, which is kind of like scratch work for a proof. You kind of just start off by saying, okay, well, I need to show this, so now I need to write it out formally. Proofs are a logical flow of writing and mathematical notation. So just remember that it's kind of like a little mini essay just stating why you believe something is the way it is by backing it up with mathematical statements and facts, theorems, and things that are proven true. So in order to do this, the first thing that we're going to do is we're going to say, suppose that f of A equals f of B. That's my first step. Then this implies the following. So we'll say the following. Since we're given the function here, and we're saying that f of A equals f of B, I'm going to say 2a minus 3 equals 2b minus 3. That's exactly what I have written there. I'm just replacing it with my function value. Now, doing some algebra, we have 2a equals 2b by adding the 3. So if we add 3, we get 2a equals 2b. Divide by 2, divide by 2, a equals b. Therefore, f of x is 1-to-1. And we can put our little tombstone. You could also just say f is 1-to-1 because technically that's the name of the function. F is 1-to-1. Okay, so you just have to do some algebra and kind of explain your steps, really. That's it, right? That's really all I did, and I just used the definition of proving something is 1-to-1 by saying, let f of A equal f of B, and then this implies the following. Doing some algebra, I get A equals B, which is exactly what the theorem states in the definition, so therefore the function is 1-to-1. Okay, let's try it for this h of x. So we say, suppose, now you could also say let, assume, say, whatever you want to say. It really doesn't matter. It's just, it doesn't matter. So suppose f of A, or we should say h of A equals h of B. Then a squared plus 1 equals b squared plus 1. By algebra, we have a squared minus 1 equals b squared. Taking the square root of both sides, we get a equals plus or minus b. This is a problem because we needed to show a equals b. So since a does not equal b, since f of A equals f of B yielded A equals plus or minus B, comma, it is not necessarily the case that A equals B for all that A equals B. Therefore, F, or we should say H. I should say H here. They're all H. H is not 1, 2, 1. Now, this is kind of like a method of disproving, right? But you could also just say counterexample, right? And then just say that whatever you want to do, right? Plug in something and get some other values out. Really plugging in like y-ish, or plugging in, you could say counterexample, A equals 1, B equals -1, right? That's a counterexample. You can show that you'll get the same value, right? You'll get the same y's, but they're not the same x's. So that's a good example to do. Okay, so that's the idea behind one-to-one. So you want to make sure that you're comfortable with, figuring out if a function is one-to-one. Okay, so inverses. In math, anything that undoes something else is considered an inverse. And so we use inverses in our everyday life, but you probably haven't really thought about it. So, for example, multiplication has an inverse, right? And we call it division, right? Division and multiplication undo each other. And you learn this from pretty young, like a younger age, right? That they undo each other. And so we can write it as 5 to the -1 times 5, right, equals 1. And we're interested in this identity element. Now, what identity really means is that if you were to multiply 5 and 1 together, you're going to get back the original element that you started with, which is 5, right? 5 times 1 is just 5. And so, essentially, when you're in the multiplication realm of operations, you're interested in finding this identity element that allows you to do the operation on any element to get back that same element. So I know that's kind of a lot of information, but that's just what an identity element does. And elements, right, are just numbers, just kind of in numbers that are specifically classified in whatever set you're working in. So we call 5 to the -1 the multiplicative inverse. Now this is the technical term of division, right? So there's issues with this kind of idea, right? What happens when you have 0? Can you do 0 and find its inverse? And, the answer is no, right? You can't divide by 0. So it causes a lot of issues. This is a huge issue in group theory. That's where all of this idea comes from. And so if you're interested in that, you can just give it a quick search and search up group theory, and you'll find a bunch of information about multiplicative inverses and these kinds of ideas, because a lot of times you study it in more broad sense versus just exact concrete examples. Okay, the other thing that we have is addition, right? Addition is our other kind of operation. So we need to find some type of an inverse that gets us back the identity. Now the identity for addition is 0. If you add 0 to anything, you always get back what you started with. So 5 plus 0 equals 5. So 0 is going to be our identity element. Now, this is a tough thing to think about because we need to make sure that depending on what we're working in, we have that identity element. So we call this the additive inverse, which is subtraction, right? So technically speaking, in math, there is no such thing as division and subtraction, right? It's just multiplicative inverse and additive inverse. But that's a debate for another day. So anyway, so we have that kind of ideas, and we want to use that into functions, right? These are examples in numbers, and we want to talk about functions, right? That's what we're interested in. So the same idea with functions, but a little bit different, right? Because we're trying to figure out, now we need to figure out what the identity element is for functions, and also what is the operation that we're doing. Because we're not going to want to multiply functions together. We're not going to want to divide or subtract or add or do anything like that. So if you remember from when we talked about different kinds of functions, we were learning about composition of functions. And that's going to be the main operation that we are interested in doing. So if you remember, composition of functions comes from section 1.8 is composition of functions. So if you want to brush up on composition of functions, that's the section to do so. So let's talk about inverses. Now, a function needs to be one-to-one in order for an inverse to exist. And the reason being is that there's a lot of issues when we talk about inverses, because what it does is it essentially swaps the domain and range around. And so you have to be really, really careful, because there's certain functions that don't have the same domain and range. And so if you remember, right, there's been questions in the past where I asked, or maybe, does there exist functions with the same domain and range, right? And those are kind of why we're interested in asking those questions. It's because now we really care about domain and range of two different functions if we're asking the inverse kind of question. So if for two functions to be inverses of each other, they have to satisfy this condition. When you compose the two functions together, you need to get back just x, which is going to be the identity element for composition. So this is just saying that f of g of x, right, the composition of f and g, is you get back x for all x in the domain of g. Whatever function you're inputting into the other function is the domain that you care about. Now you have to be careful, because we do use special little notation to indicate inverses. F to the negative 1 power. Now, up here, when we talked about our multiplication, it was fine that we could write it like this with the fraction. It's completely fine because it's a number. And we know that that is a legal math term to do. When we have a negative 1 as the exponent, it's completely fine. The problem is when you have a function and you have that negative 1, it does not mean that you can just flip the function over. That's not what it's saying. It's saying that this is the inverse. So even though this one we can do that, this is technically the inverse term. This is technically the inverse. It's just that it so happens that we're using numbers that we can use that special negative 1. We cannot do that for functions, so don't even try. Do not confuse this with the exponents. It's completely different. Working with real numbers, real tangible numbers, is very different than working with functions. Functions are more arbitrary. They have bigger, different properties versus just numbers. Okay, so these questions are a little bit computational, so they might take you a couple minutes to do, a little bit longer problems, but they're more manageable. They're not terrible, all right? So first thing, we have these two problems here, and we need to determine if they're inverses of each other. Now, another thing that we want to keep in mind is their domain, right? We want to make sure that we understand. The domain of f is going to be all real numbers. Even though it's a fraction, the 2 is in the denominator. It's not going to make a difference. Same thing over here. We have a linear domain, negative infinity to infinity. It's completely fine, okay? So it's completely fine. Okay, so let's plug them in to see what we get. So we need to compute f of g of x first. That's our first step. So we will get f of g, which is 2 times x minus 6, equals... Now, remember, when we're composing two functions, we're replacing them. So we have 2 times x minus 6 plus 6 all over 2. So we should get 2x minus 12 plus 6 all over 2, which would reduce down to 2x minus 6 over 2, which reduces down to 2 times x minus 3 over 2, which does not give us x back. So since this does not give us x back, we can stop here and we can comfortably say that this is not going to be inverses of each other. So the answer is no. Since this formula and this definition says that both of the conditions have to be true, once one fails, they both fail. So for this one, the answer is no. So this is not, they are not inverses. So let's determine if these, let me rewrite this one though. Minus plus 1. Okay, let's see if these are inverses of each other. So I don't want this one. I want plus 1 here. 1 plus this. So let's see if these are inverses of each other. So the first thing we need to do is find f of g of x. That's our first step. So we get f of 1 plus x to the third, which is the cube root of 1 plus x to the third minus 1, which gives us the cube root of x to the third, which gives us x. Now, something that we didn't mention here was the domains. The domain of this guy is all real numbers. Remember, cube roots, we don't care if they're negative. That's allowed. Same thing with this guy. Domain of this guy is all real numbers. So we can kind of start off saying that there can be an inverse since their domains match. Okay, what about g of f of x? Let's make sure this matches. So we have g of the cube root of x minus 1. Now we'll have 1 plus the cube root of, let me plug this in, plus the cube root of x minus 1 all raised to the third. So we get 1 plus x minus 1, which gives us x. So therefore, f and g are inverses, since they matched. Okay, how about this last one? Determine if the square root of x plus 5 and x squared minus 5 are real numbers. Let's talk about their domain. So domain, let's see what we get. We're going to get, for our domain for our square root is going to be negative 5, hard bracket, to infinity. And this one is going to be all real numbers. So right off the bat, we're going to have to be careful here because we need to make sure that this works when we're trying to show inverses. So f of g of x, we get the square root, or we should say f of x squared minus 5 equals f square root of x squared minus 5 plus 5. Which gives me the square root of x squared, which gives me plus or minus x. Here's where we have to be very careful. Now, if you were to drop that square root there, right, and you forgot to write plus or minus, you might think that this would be fine. Because if I did g of f of x, I get g of square root x plus 5 equals x plus 5, the square root of this, squared minus 5, which gives me x plus 5 minus 5, which gives me x. Now, you might think that this is okay, but logically speaking, there is a flaw. This is the issue. You cannot get plus or minus x back. That's not how this works. It needs to be just plain x. Now, this also makes sense because their domains do not match up, which means that they can't be inverses of each other because it's not going to work. Remember, the domains kind of have to be very similar, and their ranges have to be very, in a specific way that the ranges would have to kind of switch. Because remember, inverses kind of swap their domain and ranges. So you have to be careful that whenever you see this happen, and when you're taking square roots, you need to be very careful. Now, cube roots, it doesn't matter, right? We can have negative cube roots, and it doesn't really matter. That's why it's fine. But whenever you start having parabolas and such, you have to be very, very, very careful. Okay, so if we were not given the inverses and we were asked to find an inverse of a function, we're able to do this. We can do this. So we do this series of steps. You have to replace f of x by y, swap the x and y's around, solve our y, and replace with f to the negative 1 of x, or that inverse function notation. So let me show you how to do one of these. So we have f of x equals 3x minus 1. This is perfect example, right? Our domain is going to be negative infinity to positive infinity here. It's perfectly fine. It's great. So what we have to do now is we need to follow these series of steps. So we replace f of x by y. Step 1. We get y equals 3x minus 1. Now, we swap x and y. This is what we're doing. Step 2. Swap them. So we get x equals 3y minus 1. That's what I mean by swapping. Now, step 3. Solve for y. So, I get x plus 1 equals 3y. Y equals x plus 1 over 3. Okay? Now, I need to replace my y with f to the negative 1. So, f of negative 1 of x equals x plus 1 over 3. Now, you can check to see if this is going to work. You can replace it and put them back into each other and check. But this is going to work. This will work. Okay, now we need to find the inverse of this function. Find the inverse of f of x equals 3 minus x over x plus 3. So this one's going to be a little bit more tricky. So let's do the first step. Step 1. We replace f of x with y equals 3 minus x, x plus 3. Step 2. Swap. So we get x equals 3 minus y over y plus 3. Okay, step 3. We need to solve for y. So I'm going to multiply both sides by y plus 3. So I get x times y plus 3 equals 3 minus y over y plus 3 times y plus 3. This is going to cancel. So I'm now left with x times y plus 3 equals 3 minus y. Now I'm going to multiply and distribute this x through. So I get xy plus 3x equals 3 minus y. I'm going to add this y over. So I get xy plus 3x plus y equals 3. And now I'm going to move this 3x over. So I get xy plus y equals 3 minus 3x. I'm going to factor a y out. So I get y times x plus 1 equals 3 minus 3x. Divide by x plus 1. Divide by x plus 1. So I get y equals 3 minus 3x all over x plus 1. Now, I can't forget my last step, which is step 4. F to the negative 1 of x equals 3 minus 3x all over x plus 1. This is the inverse. So you have to be very careful. Some things that don't have inverses are parabolas because they're not one-to-one. So remember, it has to be one-to-one. So you have to check for the functions one-to-one first, and then go from there. And so that's going to be section 3.1, determining inverses.